The universe is expanding, and energy is disappearing. This is the cosmic ledger problem, a fundamental crack in our understanding of physics, where the first law of thermodynamics seems to break down on the grandest scale. By the end of this journey, you will see the cosmos not as a static stage, but as a dynamic, energy-eating entity that challenges reality itself. We will uncover where that lost energy might be hiding and how its disappearance reshapes the ultimate fate of everything. What does it mean for our most trusted laws of physics if the universe itself cannot keep its own books? Space itself is stretching, and with every passing moment, the cosmic fabric grows a little larger. This is not an explosion flinging galaxies outward like shrapnel. They are not racing through a static void. Instead, the stage upon which they sit is itself expanding, carrying them apart in a grand, silent drift. This fundamental idea comes from Einstein's theory of general relativity, which paints gravity not as a force but as the warping and stretching of spacetime. We see this expansion written in the light of distant galaxies. Their light waves stretch to redder colors as the space between us and them elongates, a direct observation confirming the universe is in a state of perpetual, dynamic flux. Cosmologist Sean Carroll often stresses that this is not a passive background event. It is an active process, relentlessly reshaping our entire cosmic environment. To understand it, picture a loaf of raisin bread baking in an oven. The raisins are the galaxies, and the dough is the fabric of space. As the dough rises, it expands uniformly, carrying every raisin away from every other raisin. No single raisin is the center. From the perspective of any raisin, all the others are moving away. This is our universe, a cosmic loaf that has been rising for nearly 14 billion years. And we now know this expansion is not slowing down. It is accelerating, driven by a mysterious influence we call dark energy. Observations of distant supernova revealed that these stellar explosions were fainter than expected, meaning they were farther away than they should have been in a coasting universe. The expansion is speeding up. This acceleration deepens the mystery immeasurably. If space is stretching, and it is doing so at an ever-increasing rate, what happens to all the energy that was already here? The light waves traveling across the cosmos get stretched too, their wavelengths lengthening, their energy slowly, inexorably draining away. Where does that energy go? This is the very heart of the cosmic ledger problem, a fundamental discrepancy appearing on the grandest balance sheet of all. This creates a profound cosmic accounting error. Think of the universe as a vast, meticulous ledger book, one that must always be in perfect balance. For generations, we have trusted the first law of thermodynamics, a fundamental rule stating that energy cannot be created or destroyed. It can only change form. The total energy of a closed system must remain constant. Yet when we apply this bookkeeping to the entire cosmos, the numbers do not add up. The universe, it seems, is running a continuous energy deficit. Energy appears to be vanishing right before our eyes. The brilliant physicist Richard Feynman pointed out that in the curved and dynamic spacetime described by general relativity, the simple, global conservation of energy we learned in school is not so clear-cut. The problem manifests in the very light that allows us to see the universe. As a photon, a particle of light, travels across the expanding cosmos, the space it moves through stretches. This stretches the photon's wavelength, shifting it toward the red end of the spectrum. But a longer wavelength means lower energy. So with every million years of its journey, the photon is steadily losing its vigor. This is not energy being transferred to another object. it is not being converted into another type. It is simply fading away, diluted by the stretching void. This happens on a colossal scale. The cosmic microwave background radiation, the afterglow of the Big Bang, has been traveling for over 13 billion years. In that time, the expansion of space has sapped it of immense amounts of energy. Where did that energy go? The answer depends entirely on your perspective. Locally, the rules still seem to hold. In your laboratory, on Earth, or even within our solar system, energy is conserved. But take a global, cosmic view, summing up the energy of the entire universe, and the ledger falls out of balance. This is the core of the cosmic ledger problem. How can our most trusted law of physics hold true in our backyard, yet fail when applied to the cosmos as a whole? This dilemma forced physicists to reconsider the very meaning of energy and set the stage for a century of cosmological debate. Edwin Hubble's monumental discovery did more than just reveal an expanding universe. It tore a hole in our most fundamental understanding of physics. Standing at the Mount Wilson Observatory in the 1920s, Hubble meticulously measured the light from distant nebulae. He found their light was not just red, but redshifted, a telltale sign they were receding from us. This observation shattered the long-held belief in a static, eternal cosmos, replacing it with a dynamic, evolving reality. In the wake of this revelation, a profound question emerged. If the universe is stretching, what happens to the energy within it? The initial assumption among physicists was a comforting one. Surely, they thought, the principle of energy conservation must hold true for the cosmos as a whole. Energy could not simply vanish. But this classical intuition was about to collide with a new and bizarre reality described by Einstein's general relativity. In this new framework, the very idea of a global energy balance became slippery. Energy conservation, it turned out, depends on a smooth, unchanging background of space and time. But general relativity described a universe where that background was itself dynamic and curved, warped by matter and energy. Albert Einstein himself grappled with this. He introduced a fudge factor into his equations, the cosmological constant, to force the universe into a static state he believed was necessary. He later famously called this his biggest blunder, not because the idea was wrong, but because he had missed the chance to predict the universe's expansion. That constant, which we now associate with dark energy, hinted at a dynamic balance of energy on a cosmic scale, something that did not fit the old, simple rules. This confusion gave rise to alternative models like the steady-state theory. Proposed by Fred Hoyle and others, this elegant idea suggested that as the universe expanded, new matter was continuously created out of nothing to maintain a constant density. In this model, the cosmic ledger was balanced not by conserving energy, but by constantly adding to the credit side. It was a beautiful, philosophical solution, but it was ultimately disproven. The discovery of the cosmic microwave background radiation in the 1960s provided definitive evidence for a hot, dense beginning. The Big Bang and the steady-state model faded away. The universe was not in a steady state. It had a history, and its expansion was real. The puzzle only deepened with the development of quantum field theory in curved spacetime. Pioneers like Stephen Hawking explored the wild implications of applying quantum rules to the warped geometry of general relativity. Hawking showed that even black holes, the ultimate vacuums, could not hold onto their energy. They could slowly evaporate, radiating particles and energy back into the universe. This was a stunning revelation. Energy seemed to be tied inextricably to the shape and evolution of space itself. Consider the theory of cosmic inflation, which proposes a period of unimaginably rapid expansion in the universe's first moments. During this inflationary burst, the universe expanded faster than the speed of light, and a tremendous amount of energy was pumped into the fabric of spacetime itself, seeding all the structure we see today. Yet, if you tried to account for that energy using standard bookkeeping, you would find it seemingly appeared from nowhere. Looking back at this century of struggle, a clear lesson emerges. Our physical laws are not absolute, immutable truths written in stone. They are descriptions of reality that are profoundly shaped by the scale and environment in which we apply them. The failure of the steady-state model and the success of inflation taught us that the universe is far more dynamic and strange than we ever anticipated. The very concept of energy, so clear and dependable in a lab on Earth, becomes a ghostly, elusive quantity when faced with the expanding stage of the cosmos. These historical efforts to patch the cosmic ledger did not fail. They paved the way for the radical frameworks we are exploring today. Einstein's theory of general relativity does not just describe gravity. It completely rewrites the rules of the cosmic energy game. Think of a roller coaster car moving along a twisted, warped track. On a flat, straight section, you can easily calculate its energy using simple, reliable formulas. But when the track curves sharply upward or plunges into a deep valley, those simple calculations break down. The energy of the car seems to change not because energy is magically appearing or vanishing, but because the shape of the track itself, the very geometry of its path, is part of the equation. This is the world of general relativity. The space-time through which everything moves is not a static, flat stage. It is a dynamic, curving landscape. And in such a landscape, the neat, global conservation of energy we learn in school simply does not apply. As physicist Kip Thorne and others have clarified, in the curved spacetime of general relativity, there is no single, universal definition of energy that guarantees its conservation across the entire cosmos. Energy is a local phenomenon, faithfully conserved in small, flat regions of space, but its global sum for the whole universe is not a fixed number. This profound shift is encoded in the mathematics of the theory, specifically in the stress-energy tensor. This is not a single number, but a complex mathematical object that describes the density and flux of energy and momentum at every point in spacetime. It tells spacetime how to curve through the Einstein field equations, and these equations show that while the stress-energy tensor is covariantly conserved, meaning energy and momentum are conserved in any small, local neighborhood, this local bookkeeping does not translate into a global law for the entire universe. The expansion of the universe is the ultimate demonstration of this. The Hubble parameter, which measures the rate of cosmic expansion, is not just a number. It is an active agent in the energy story. As a photon travels for billions of years across the expanding cosmos, the space through which it moves stretches. This stretches the photon's wavelength, causing the cosmological redshift we observe. A longer wavelength means lower energy. The photon arrives at our telescopes significantly weaker than when it began its journey. The energy is gone. It has not been transferred to another particle. It has been lost to the gravitational field, to the evolving geometry of the universe itself. We see this with light from incredibly distant quasars, whose brilliant energy is sapped by the vast, stretching void. So, is energy truly destroyed? Or is our entire method of cosmic accounting fundamentally flawed? The answer may lie not in the large-scale fabric of spacetime, but in the tiny quantum world that underpins it all. Dark energy is the phantom in the cosmic ledger, an influence so dominant it dictates the very pace of the universe. It makes up about 68% of the universe's total energy content, a fact cemented by the Nobel Prize-winning work of cosmologists like Adam Rees. By observing distant supernova, his team confirmed that the expansion of space is not just continuing, it is accelerating. This acceleration is driven by dark energy, a mysterious component that acts like a negative pressure, relentlessly stretching the fabric of spacetime. The nature of this entity is encoded in its equation of state, a number close to -1. This specific value has a bizarre consequence. As the universe expands and volume increases, the density of dark energy does not drop. It remains constant. Think of a bank account where you continuously withdraw money, yet the balance never goes down. It simply grows to fill the void. In the cosmic context, as space stretches and the volume of the universe grows, more dark energy appears to maintain the same energy density everywhere. From our classical perspective, this looks like energy is being created from nothing, directly challenging the first law of thermodynamics. The leading candidate for dark energy is the cosmological constant, a concept Einstein first introduced and then discarded. This model treats dark energy as an immutable property of the vacuum of space itself, a fixed energy density that does not dilute. If this vacuum energy is real, then the ledger problem becomes a fundamental feature of reality. Energy is not being destroyed in one place and created in another. The entire framework of global conservation is the wrong tool for the job, but the cosmological constant is not the only possibility. Some theories propose a dynamic form of dark energy called quintessence. Unlike the static cosmological constant, quintessence could change over time, its energy density slowly evolving. This would introduce a different kind of accounting, one where the energy flow might be more complex, perhaps even allowing for some form of conservation to be restored under a new set of rules. Yet despite these alternatives, the observed persistence of dark energy forces us to confront a deep question. How can our most trusted laws of physics reconcile with a universe that seems to generate energy as it grows? To find an answer, we must look beyond the energy of things within space and consider the energy of space itself, hidden in the gravitational field. Gravitational potential energy holds a secret that deepens the cosmic ledger problem. On Earth, the rules are simple. When you lift a ball against gravity, you do work. The energy you expend is stored in the ball-Earth system as gravitational potential energy. It is a neat, localized transaction, but in an expanding universe described by general relativity, this familiar concept breaks down completely. The gravitational field is not a separate entity. It is the very curvature of spacetime itself, and the energy associated with it cannot be pinned down to a specific location. This is not a flaw in the theory, but one of its most profound features. Experts like Sean Carroll emphasize that in cosmology, the gravitational field itself acts as a vast cosmic battery, storing and releasing energy in ways that defy our conventional bookkeeping. The equations that govern the evolution of the entire universe, the Friedmann equations, try to account for this. They incorporate a term for the curvature of space, which is intimately tied to gravitational energy. Yet this energy does not conserve itself in the usual, simple sense. Think of kinetic and potential energy in this cosmic context. As galaxies are carried apart by the Hubble flow, the smooth expansion of space, they are like runners on a track that is itself stretching. Their motion relative to the stretching fabric is minimal, so their kinetic energy from the expansion is essentially zero. But their gravitational potential energy is changing dramatically. As the distance between them increases, their mutual gravitational potential energy grows. In a closed system, this increase would be perfectly balanced by a decrease in kinetic energy. But the universe is not a closed system in that classical sense. The expansion of space itself is doing work. inputting energy into the system and allowing this potential energy to grow without a corresponding drop elsewhere. This is where the redshift of light connects directly to this gravitational energy story. A photon flying from one galaxy to another is like a ball rolling up an ever-steepening hill. The expanding space between them acts like a continuous gravitational slope. As the photon climbs, it loses energy, its wavelength stretching to the red. That lost energy is not transferred to the galaxies. It appears to be transferred to the gravitational field, absorbed by the evolving geometry of the universe. But because that gravitational energy is not a localized quantity we can easily measure, it simply vanishes from our ledger. The potential energy of the galaxies increases, the energy of the photon decreases, and there is no neat global balance to show for it. The energy has seemingly leaked away into the cosmos. Is this leakage a real physical effect, or merely a limitation of our models and our insistence on using classical accounting for a relativistic universe? To answer that, we must peer into the quantum fabric from which spacetime itself may be woven. This quantum bubbling hints at a hidden energy budget woven into the fabric of reality itself. To peer into the cosmic ledger, we must descend to the smallest possible scales where the rules of quantum mechanics reign. Here, the very idea of empty space dissolves. What we call a vacuum is not a barren, static void. It is a seething, dynamic sea, alive with fleeting activity. Quantum field theory tells us that pairs of virtual particles and antiparticles continuously pop into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This ceaseless dance of creation and destruction is known as vacuum fluctuation. The legendary physicist John Wheeler described the spacetime at this scale as a quantum foam, a turbulent, churning geometry where the smooth fabric of the cosmos breaks down into a probabilistic frenzy. These fluctuations are not just a mathematical curiosity. They have real, measurable consequences, and they contribute an energy density to the universe that must be accounted for in our cosmic ledger. The Casimir effect provides a stunning demonstration. If you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they will be gently pulled toward each other. Why? Because the space between the plates is so narrow that it restricts the kinds of virtual particles that can flicker into existence. Outside the plates, the full spectrum of fluctuations can occur, creating a subtle pressure that pushes the plates together. This measurable force is direct evidence that the vacuum is not empty. It possesses a real physical energy. Similarly, Stephen Hawking showed that the intense gravitational field at the edge of a black hole can wrench these virtual particles apart, preventing their annihilation. One particle falls into the black hole while the other escapes as real radiation, slowly causing the black hole to evaporate. This is Hawking radiation, a process powered entirely by the energy of the quantum vacuum. So we know this vacuum energy is real. The problem, and it is a colossal one, arises when we try to calculate how much of it there is. When theorists add up the contributions from all possible quantum fields, the result is an energy density so immense it should have caused the universe to expand at a rate that would have torn apart atoms nanoseconds after the Big Bang. The calculated value is about 120 orders of magnitude too large. This staggering mismatch between prediction and observation is known as the cosmological constant problem, and it represents the worst theoretical prediction in the entire history of physics. It suggests we are missing something profound, a symmetry or a principle that cancels out almost all of this vacuum energy, leaving behind the tiny, residual amount we call dark energy. Now consider what happens to this quantum foam as the universe expands. The stage itself is stretching, and this changes the dynamics of the bubbling vacuum. Think of the vacuum as a pot of water coming to a boil. The bubbles are the virtual particles. If you suddenly enlarge the pot, the boiling activity changes. In an expanding universe, the stretching of space can actually promote some of these virtual particles into real, lasting particles. This is the essence of effects like Unruh radiation, where an accelerating observer detects a warm bath of particles in what a stationary observer sees as empty space. In cosmology, the expansion of the universe acts as a kind of accelerator, and it can literally create particles and energy from the evolving quantum fields. So, is this the hidden ledger? Is the energy lost by a redshifted photon somehow transferred to the quantum vacuum, fueling the creation of new particles? The answer remains elusive. The connection between the large-scale loss of energy and the small-scale gain from particle creation is not a simple one-to-one transaction. It points toward a deeper truth that energy conservation on a cosmic scale may be an emergent property, not a fundamental law. To see if the books can ever truly balance, we must step back and view the entire universe through the lens of thermodynamics. The universe is not just a collection of galaxies. It is a colossal heat engine, and we are living inside it. To understand the cosmic ledger, we must apply the laws of thermodynamics to the cosmos as a single, vast system. The first law of thermodynamics is our familiar energy accounting rule. It states that the change in a system's internal energy is equal to the heat added to it minus the work done by the system. In an expanding universe, the stretching of space itself is doing work on the cosmic fabric, relentlessly pushing galaxies apart. But what is the source of this work? Where is the heat flow that should balance this cosmic expenditure? From our global perspective, there is no obvious input or output. The work is being done, but the energy to pay for it seems to come from nowhere, creating the appearance of a fundamental violation. The physicist Roger Penrose has deeply explored these thermodynamic puzzles, focusing on the role of cosmological horizons and entropy. A cosmological horizon defines the ultimate limit of what we can see, the boundary beyond which light has not had time to reach us since the Big Bang. As the universe expands, this horizon changes, and with it, the maximum possible entropy the universe can contain. Entropy is a measure of disorder, and the second law of thermodynamics insists it must always increase. This is the one law that seems unshakable, even on a cosmic scale. The expansion of space guarantees this increase. Think of a gas expanding into a larger volume. It cools down and its particles spread out, becoming more disordered. The universe behaves in exactly this way. Its expansion is adiabatic, meaning no heat flows in or out from some external source because there is no outside. As space stretches, the radiation within it, like the photons of the cosmic microwave background, is stretched too. Their wavelengths lengthen and their energy drops. The universe cools. This is why the afterglow of the Big Bang, once searingly hot, is now just a faint whisper of microwaves at a temperature only 3 degrees above absolute zero. Its energy density has plummeted, so energy is lost, yet total entropy skyrockets. How can both be true? Imagine the universe as a giant cosmic piston. The expansion is the piston moving outward, doing work by creating more volume. In a normal engine, this work would be balanced by heat flowing from a hot reservoir to a cold one. But our universe has no external reservoirs. The work of expansion is paid for by the internal energy of the universe itself, primarily the energy stored in the gravitational field and the vacuum. The energy lost by a cooling photon is not destroyed. It is converted into the work of creating new space. which in turn increases the total entropy of the cosmos by creating a larger playground for disorder. This is how thermodynamics reframes the ledger problem. We have been looking for a simple balance sheet of energy in and energy out. But thermodynamics tells us the story is more about the transformation of energy into work and the inevitable rise of entropy. The cosmic ledger is not balanced in terms of energy conservation. It is balanced in terms of thermodynamic potentials, where the drive toward greater disorder powers the entire engine. This bizarre accounting forces us to consider a concept that seems like pure science fiction, the idea of negative energy. Negative energy sounds like a concept from science fiction, but it is a serious proposal for balancing the cosmic books. In the strange mathematics of general relativity, gravitational potential energy is not always positive. In fact, it is almost always negative. Picture a deep well from which you must expend energy to climb out. An object sitting at the bottom of that gravitational well is considered to have negative potential energy relative to the freedom of empty space. Now apply this to the entire cosmos. The universe is filled with positive energy, the mass of stars, the light of galaxies, the seething quantum vacuum. But it is also filled with gravity, and the gravitational field binding everything together carries a colossal negative energy. What if these two sums perfectly cancel out? The physicist Alan Guth, a pioneer of inflationary theory, famously proposed this zero-energy universe hypothesis. He suggested that the total energy of the cosmos could be precisely zero, because the positive energy of all matter and radiation is exactly cancelled by the negative energy of the gravitational field. This is a breathtaking idea. It means the universe could have come from nothing, requiring no net energy for its creation, the ultimate free lunch as Guth described it. But how does this work in an expanding universe? As space stretches, new volume is created. With it comes more matter and radiation, which represents positive energy. Yet the gravitational field also expands, and its negative potential energy becomes even more negative. In this grand cosmic transaction, the two might offset each other in a continuous dance. The ledger always reads zero. Think of it like taking out a mortgage to buy a house. The house is your positive asset, while the mortgage is your negative debt. Together, your net worth is zero. Now, imagine the bank continuously increases your mortgage line exactly in step with the appreciating value of your house. Your assets grow, but so does your debt, and your net worth remains perfectly balanced at nothing. This is the zero-energy universe in expansion, but this elegant idea faces serious criticisms. The primary challenge is defining the total negative gravitational energy of the entire universe in a rigorous, global way. In the curved and dynamic spacetime of general relativity, there is no single, agreed-upon method to sum up this negative energy across all of space. It is a mathematically slippery concept. Furthermore, inflationary cosmology, which Guth helped develop, provides a tantalizing example. In this model, our entire observable universe could have sprouted from a tiny quantum fluctuation in a primordial vacuum. That fluctuation borrowed energy, but if the total energy was zero from the start, no fundamental laws were broken. The positive energy of the new particles was instantly balanced by the negative gravitational energy of the new spacetime they created. So, does negative energy resolve the cosmic ledger problem? In one sense, it offers a profound philosophical answer, suggesting there was never any energy to lose in the first place. Yet, it complicates our understanding immensely, replacing a simple missing number with a deep question about the very nature of nothingness. To see if this balance is a mathematical trick or a fundamental truth, we must investigate the beautiful underlying symmetry that gave us the concept of conservation in the first place. The very foundation of energy conservation rests on a beautiful, hidden symmetry of the universe. In the early 20th century, the mathematician Noether uncovered a deep connection between the symmetries of nature and the laws of conservation. Her brilliant theorem states that for every continuous symmetry in the laws of physics, there is a corresponding quantity that is conserved. The conservation of energy, our trusted first law of thermodynamics, emerges directly from a specific symmetry, time translation symmetry. This means the laws of physics do not change from one moment to the next. An experiment performed today will yield the same result as the same experiment performed tomorrow, because time itself is uniform. This uniformity guarantees that energy is neither created nor destroyed. But what happens when that perfect symmetry is broken? Our expanding universe does exactly that. As space stretches, the very fabric of time is warped. Cosmological time is not the uniform, ideal ticking of a perfect clock in empty space. It is intertwined with the evolving, stretching geometry of the cosmos. Experts like Leonard Susskind point out that in the curved spacetime of general relativity, this crucial time symmetry is absent on a global scale. The universe yesterday was denser and hotter than the universe today. The laws of physics, while still locally consistent, operate on a stage that is fundamentally different from one epoch to the next. Because time translation symmetry is broken by cosmic expansion, Noether's theorem no longer mandates that energy must be conserved for the universe as a whole. This is not a failure of physics, but a consequence of its deepest principles. We can visualize this with the stretching rubber sheet. Imagine clocks placed at different points on the sheet. As the sheet expands, the distance between the clocks increases. More profoundly, the rate at which time flows for each clock is subtly influenced by the overall expansion. They do not tick in perfect, synchronized unison with some master cosmic clock. There is no such universal time. This is captured mathematically in the Friedmann-Lemaitre-Robertson-Walker metric, which describes the large-scale structure of our homogeneous and expanding universe. In this framework, a translation in time is not a symmetry of the spacetime itself. You cannot shift the entire universe to an earlier time and have it look exactly the same because it was smaller and denser. Since the symmetry is broken, the conservation law it would have guaranteed, the global conservation of energy, simply does not apply. This directly impacts the stress-energy tensor, the mathematical description of all the energy and momentum in the universe. In a static, flat spacetime, certain operations on this tensor would confirm global energy conservation, but in our dynamic cosmos, those operations fail. The energy described by the tensor is not conserved because the background against which it is measured is itself changing, so the cosmic ledger was never broken. We were simply trying to apply a local accounting rule to a system that fundamentally lacks the symmetry required for that rule to hold. The energy lost by a redshifted photon is the direct price paid for this broken symmetry, a signature of a universe where time itself is part of the dynamic fabric. This profound link between symmetry and conservation leads us directly to the most explosive period of cosmic evolution, where these rules were stretched to their absolute limit. The most extreme violation of the cosmic ledger occurred not today, but in the universe's very first moments. For a fleeting fraction of a second, the cosmos underwent a growth spurt of unimaginable ferocity, a period known as inflation. During this epoch, the universe did not just expand, it exploded in size, doubling its volume again and again in a cascade of exponential stretching. This process, driven by a hypothetical scalar field called the inflaton, smoothed the cosmos to the uniformity we see today and set the stage for everything to come. But it also created the ultimate energy puzzle. The inflattened field was trapped in a state of high potential energy, like a ball perched at the very top of a plateau. This energy density acted as a powerful engine for expansion, and because it remained nearly constant as space swelled, the total energy of the universe appeared to skyrocket. More space was created, and with it more of this inflationary energy. Cosmologist Andre Linde, a key architect of this theory, describes how the quantum fluctuations in this field were the crucial ingredient. As the inflattened field fluctuated at the quantum level, these tiny ripples were stretched to astronomical sizes by the hyper-expansion, becoming the seeds for all the galaxies and cosmic voids we observe. The energy for this entire cosmic structure was effectively borrowed during this wild inflationary phase. But how can energy be borrowed if the total amount is not conserved? The process of reheating marks the end of inflation, when the inflattened field finally rolled down its potential hill. Its pent-up potential energy converted violently into kinetic energy, and then into a hot, dense soup of particles and radiation, filling the newborn universe with the raw material for stars and planets. Think of it like a balloon inflating at a frantic, unstoppable rate. The air pressure inside, representing the inflattened's energy density, stays constant even as the balloon's volume becomes astronomically large. From our classical perspective, the total amount of air, the total energy, has increased fantastically. Yet, the expansion itself also generated gravitational waves, ripples in spacetime that carry energy away from the system. So, did inflation simply create energy from nothing? The mathematics of general relativity allows for this, as the gravitational field's negative energy may have balanced the books, resulting in a net energy of zero even during this explosive growth. The true answer may be written in the oldest light we can see, the cosmic microwave background, where the imprints of those stretched quantum fluctuations serve as a permanent record of the universe's most dramatic accounting maneuver. The cosmic microwave background is a fossilized whisper of creation, a snapshot of the universe as it was just 380,000 years after the Big Bang. This afterglow fills all of space, a nearly uniform glow of microwave radiation that serves as our most direct witness to the universe's expansion and its effect on energy. When scientists like George Smoot first mapped its minute imperfections, they were reading a cosmic ledger written in the cold light of the ancient sky. The most telling feature of this radiation is its perfect blackbody spectrum. It is the signature of an object in perfect thermal equilibrium, and its temperature has been dropping relentlessly for billions of years. When the cosmic microwave background was first emitted, the universe was a searing plasma at about 3000 Kelvin. Today, that same radiation has cooled to a mere 2.7 Kelvin, just 3 degrees above absolute zero. This cooling is not a passive chilling. It is the direct result of the stretching of space itself, which has diluted the energy of every single photon in that primordial fire, systematically draining its vigor across cosmic time. Each photon we detect from this background has been on an epic journey, and its redshift is a measure of the energy it has lost along the way. This energy loss is precisely quantified in the power spectra derived from missions like the Planck satellite. These intricate charts of the cosmic microwave background's fluctuations do more than just confirm the universe's age and composition. They act as a strict accounting tool, constraining our models of dark energy and inflation by showing us exactly how the energy budget has been managed. The data forcefully rules out models where energy is naively conserved, pointing instead to a dynamic, evolving geometry. A particularly subtle clue is etched into the fabric of the cosmic microwave background itself, known as the integrated Sachs-Wolf effect. As the photons of the background radiation travel toward us, they must climb in and out of the gravitational wells of vast cosmic structures, like superclusters of galaxies and immense voids. In a universe where the gravitational potential of these structures was static, the energy a photon loses falling in would be exactly regained as it climbs out. But in our accelerating universe driven by dark energy, these large-scale potentials are not static. They are evolving, decaying over time as the expansion continues. When a photon climbs out of a gravitational well that has become shallower during its journey, it does not get all of its energy back. It arrives at our telescopes slightly cooler, its energy having been sapped by the changing gravitational landscape. This faint, specific imprint of energy loss, confirmed by Planck data, is a direct observational signature of the work being done by the expansion of the universe. It is as if light itself is a messenger whose words slowly fade as it crosses an ever-widening valley, its message dimming not from the distance traveled, but from the stretching of the ground beneath its feet. So, where did that energy go? These observations tell us it was not transferred to another particle or converted into another form of matter. It was paid as a toll to the expansion, absorbed into the evolving geometry of spacetime. This forces us to consider a possibility as radical as the energy loss itself, that the true ledger of the cosmos is not written in 3 dimensions, but is projected from a 2-dimensional boundary like a cosmic hologram. Perhaps the ultimate resolution to the cosmic ledger lies not in the space around us, but on a distant, fundamental screen. The holographic principle is one of the most radical ideas in modern physics, suggesting that our perception of a 3-dimensional universe is a magnificent illusion. Everything we see and feel, every particle of matter and every quantum of energy, might be a projection from a 2-dimensional surface at the very edge of the cosmos. This is not a metaphor, it is a serious proposal that redefines where the information of reality is truly stored. The physicist Gerard T. Hooft, who helped pioneer this concept, argued that all the information within a volume of space can be fully described by a theory that lives on its boundary. Think of a hologram on your credit card. The flat, shiny surface contains all the data needed to project a stunning 3-dimensional image. In the same way, our vast, seemingly solid universe could be encoded on a distant 2-dimensional shell. If this is true, then our entire struggle to balance the energy ledger in 3 dimensions might be a fool's errand. We have been counting the money in the projection while the real accounts are kept on the boundary. This principle finds its roots in the thermodynamics of black holes. Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole, which is a measure of its hidden information, is not proportional to its volume as you might expect. It is proportional to the area of its event horizon. This Bekenstein-Hawking entropy bound was the first hint that the information capacity of a region is defined by its surface area, not its volume. A universe with a finite amount of information is a universe with a finite number of ways to arrange energy. This places a fundamental limit on the cosmic energy budget itself. The most concrete realization of this idea comes from string theory, in the form of the anti-de Sitter conformal field theory correspondence. This mouthful describes a breathtaking duality. It states that a gravitational theory operating in a hypothetical bulk space which includes gravity is completely equivalent to a conformal field theory, a quantum theory without gravity, that lives on its lower dimensional boundary. In this framework, a complex gravitational event like a star collapsing into a black hole in the bulk is exactly mirrored by a complicated but gravity-free interaction of quantum particles on the boundary. The mathematics are the same, so what does this mean for our lost energy? In the holographic view, the energy we measure within the universe is just one side of the coin. The true, fundamental description of that energy resides on the boundary. As our three-dimensional universe expands, the boundary itself is also evolving. The cosmic ledger problem, the apparent disappearance of energy from redshifted photons, might simply be a consequence of our limited, three-dimensional perspective. The energy has not vanished from the fundamental theory on the boundary. It has just become translated or reconfigured in a way that looks like a loss from our internal viewpoint. The expansion of space is then like a change in the projector's settings, altering the three-dimensional image we see, while the two-dimensional source data remains consistent and complete. Could this holographic framework finally balance the books? It offers a profound shift, suggesting that energy conservation, as we know it, is an emergent property of the deeper boundary theory. The first law of thermodynamics might be a local rule that works within the projected reality, but not a fundamental law governing the source code of the cosmos. We are like characters in a movie, suddenly realizing that the light fading from a scene is not because the sun is setting in our world, but because the projector's bulb is being dimmed from outside the screen. This holographic perspective forces us to ask if the very fabric of spacetime is an emergent property, and if so, what truly lies beneath the projection. Perhaps the answer is not to find the missing energy, but to rewrite the laws of gravity themselves. For decades, a small but determined group of physicists has pursued an alternative path, suggesting that dark energy is an illusion born from our incomplete understanding of gravity. The most prominent of these challenges is modified Newtonian dynamics, or MND, proposed by physicist Mordechai Milgrom. MND suggests that on the vast, sparse scales of galaxies, gravity does not follow Newton's or Einstein's rules. Instead, Milgrom proposed that at extremely low accelerations, the kind found in the outer rims of galaxies, the force of gravity changes. He argued that we might not need invisible dark matter or dark energy if we simply correct for a modified inertia at these cosmic scales. The idea is that the force needed to accelerate an object is not always proportional to its mass in these faint gravitational fields. This single tweak can surprisingly explain the flat rotation curves of galaxies, where stars on the outskirts orbit just as fast as those near the center, without invoking vast halos of dark matter. If gravity itself is stronger on these large, diffuse scales, perhaps the accelerated expansion of the universe could also be explained without a mysterious dark energy. But MND, while elegant for individual galaxies, struggles to explain the full tapestry of cosmological data, like the precise patterns in the cosmic microwave background. This has led to more sophisticated frameworks that embed MND-like ideas into a relativistic context, theories like tensor vector scalar gravity, which add new fields to Einstein's framework. Other approaches go even further, directly modifying the equations of general relativity. In F of R gravity, for example, the simple Einstein-Hilbert action is replaced with a more complex function of the Ricci scalar, which is a measure of how spacetime is curved. This creates new terms in the equations that can mimic the effects of dark energy, driving cosmic acceleration without an exotic substance. Similarly, Brans-Dicke theory introduces a dynamic scalar field that couples to gravity, effectively allowing the strength of gravity to change over time and across space. In these models, the expansion of the universe is not fueled by dark energy, but is a consequence of gravity's own evolving nature. How do these radical revisions handle the cosmic ledger? The results are mixed. In some modified gravity theories, you can construct a new definition of energy that is perfectly conserved. It is as if you have patched a leaky boat. The patch holds beautifully in the calm waters of a galaxy's rotation, stopping the leak of missing mass. But when you sail this boat onto the open ocean of the entire cosmos, new leaks can spring up elsewhere. A theory might conserve energy globally, but then fail to explain why galaxy clusters behave as if they are filled with dark matter. Or it might work perfectly for the cosmic microwave background, but then violate energy conservation in a different, more subtle way. Many of these models face a problem of fine-tuning, where the extra fields or functions must be chosen with exquisite, unnatural precision to match observations, a sign that the theory might be a mathematical contrivance rather than a fundamental law. So, do these alternatives offer a cleaner ledger? They shift the problem. Instead of a mysterious energy that defies conservation, we have a modified force that challenges our deepest principles. The energy lost by a redshifted photon in these frameworks might be accounted for by the changing strength of gravity or the dynamics of a new cosmic field. But this often means that energy conservation is only restored by redefining what energy means in the first place. It is a trade-off, replacing one profound mystery with another. This ongoing struggle between dark energy and modified gravity forces us to confront a pivotal choice. Is the cosmos filled with a dominant, unseen component that breaks our classical energy rules, or are we using the wrong rulebook for gravity entirely? This dilemma brings us back to a concept Einstein first wrote down, then crossed out, only for it to return as the simplest explanation for the accelerating universe, the cosmological constant. Einstein's cosmological constant, lambda, has returned from the history books to become our simplest candidate for dark energy. This tiny number, which he once discarded, represents a constant energy density inherent to the vacuum of space itself. It is not a substance that dilutes as the universe grows. Instead, it is a fixed property of nothingness, an energy that every cubic centimeter of empty space possesses forever. This constancy creates a breathtaking paradox. As the universe expands, its volume increases, more space is created, and since every new volume of space carries this same energy density, the total amount of dark energy in the cosmos grows. It is as if you had a savings account where, mysteriously, the balance grew in direct proportion to the size of the vault holding it. The bigger the vault gets, the more total money it contains without any visible deposit. From the perspective of classical physics, this looks like energy is being created from nothing, a direct challenge to the conservation law we thought was sacred. The physicist Steven Weinberg famously wrestled with the cosmological constant problem, which asks why this observed energy density is so incredibly small. When we calculate the likely energy of the quantum vacuum, the result is a number about 120 orders of magnitude larger than what we see. The universe should have torn itself apart instantly if the quantum calculation were correct. The fact that lambda is so tiny yet not zero is one of the deepest mysteries in all of physics. How does this constant energy density actually make the universe accelerate? The answer lies in its pressure. In the equations that govern cosmic expansion, the Friedmann equations, lambda acts as a persistent negative pressure. Think of the vacuum of space not as empty but as a stretched rubber sheet. A positive pressure would pull the sheet inward, slowing expansion, but a negative pressure does the opposite. It pushes outward, actively stretching the fabric. This negative pressure is the engine of acceleration. As space expands, the work done by this negative pressure input energy into the cosmos, fueling the creation of even more space and more dark energy in a self-reinforcing cycle. In a universe completely dominated by lambda, known as a de Sitter universe, this effect becomes absolute. Such a cosmos has a horizon, a boundary beyond which we can never see because space is expanding too fast for light to ever cross the gap. As time passes, new space is continuously created at this horizon, and with it, new dark energy. This is a clear mathematical case of energy non-conservation. The total energy content of the observable universe is not a fixed number. It is a quantity that grows with the volume of space itself. So where does this leave our cosmic ledger? If lambda is indeed the vacuum energy of quantum fields, then the energy is not being created in the traditional sense. It was always there, a fundamental part of the vacuum, and we are simply uncovering more of it as the universe expands, like realizing a vast, invisible ocean was beneath us all along. But this does not solve the accounting problem. It merely reframes it. The energy of a redshifted photon is still lost, while the energy of the vacuum simultaneously grows. The books do not balance in any conventional way. This forces us to look beyond energy toward a more fundamental currency. Perhaps the true ledger of the cosmos is not written in units of energy, but in bits of information and the relentless rise of entropy. Entropy is the universe's irreversible slide into disorder, and it holds a strange mirror to our cosmic ledger problem. While energy seems to vanish, entropy only ever increases. This relentless rise defines the arrow of time itself, the reason we remember the past but not the future. The physicist Ludwig Boltzmann uncovered the deep statistical heart of this process. He realized that entropy is not a mysterious force, but a simple matter of probability. A system evolves from order to disorder for the same reason a deck of cards, once shuffled, is unlikely to return to its pristine, sorted state. There are simply far more ways to be messy than to be neat. Apply this to the cosmos, and the implications are staggering. The universe began in a state of exquisite, low-entropy order, a highly improbable starting point. Ever since, it has been evolving toward a state of maximum disorder, a final equilibrium known as the heat death. The expansion of space is the engine of this transformation. Think of the universe as a room that is not only getting messier but is also physically growing larger. You start with a tidy, compact room. As the walls stretch outward, the space for disorder increases exponentially. Toys are scattered, dust settles, and the neat, ordered energy that could have cleaned the room is now dissipated, lost to the sheer effort of maintaining the growing chaos. This is what happens to the energy of a redshifted photon. Its ordered, luminous energy is not destroyed. It is converted into the work of expanding the room, a process that generates entropy, raising the overall disorder of the cosmos. The photon's lost energy is the price paid for creating more space, and that space provides an ever larger canvas for disorder to express itself. This connection is governed by a profound limit, the Bekenstein bound. It states that the maximum amount of information, and therefore the maximum entropy, that can be contained within any region of space is proportional not to its volume, but to the area of its boundary. As the universe expands, the area of our cosmological horizon increases, and with it, the maximum possible entropy the universe can hold rises. The universe is not just becoming more disordered, it is increasing its very capacity for disorder. This cosmic entropy production is driven by grand processes. The nuclear furnaces of stars convert the ordered gravitational potential energy of pristine hydrogen into light and heat, a massively entropy-increasing act. When those stars die, they scatter enriched material across space, further increasing disorder, and nothing stores entropy more efficiently than black holes. A black hole's entropy is directly proportional to the area of its event horizon. When matter and energy fall into a black hole, the information they carry, their specific order, is seemingly lost to the outside universe, replaced by a tremendous increase in the black hole's surface area. This is the heart of the black hole information paradox, a deep puzzle about whether information is truly destroyed, violating quantum principles, or if it is somehow preserved on the horizon. This paradox hints that our understanding of entropy, space, and information is still incomplete. So, does entropy hold the key to the ledger? When a photon redshifts, its energy decreases, but the total entropy of the universe increases. The energy appears to be traded for disorder. The cosmic ledger may not balance in energy, but it balances in the relentless statistical drive toward chaos. The missing energy is not missing at all. It has been converted into the currency of entropy, funding the universe's expansion and its one-way journey through time. To understand this transaction at the most fundamental level, we must finally confront the quantum nature of spacetime itself. At the very frontier of physics, we are forced to ask if spacetime itself is made of something more fundamental. Quantum gravity is the long-sought theory that aims to marry the cosmic realm of general relativity with the probabilistic rules of the quantum world. It is here, in this domain of vibrating strings and hidden dimensions, that the cosmic ledger might finally be balanced. String theory, one of the leading candidates, proposes a breathtaking shift in reality's blueprint. The fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrational patterns of these strings give rise to all the particles and forces we observe, from electrons to photons. But for the mathematics to work, these strings must vibrate in a spacetime with more than the three spatial dimensions we experience. They require extra, compact dimensions, curled up into shapes so small we never notice them. This radical framework completely redefines what energy is. Energy conservation is no longer about a simple sum of numbers in 3 dimensions. It becomes a geometric dance of vibrating strings in a higher dimensional arena. The physicist Edward Witten has illuminated how string theory in a hypothetical space known as anti-de Sitter space reveals profound dualities. In this model, a gravitational theory operating in the bulk of a higher dimensional space is perfectly equivalent to a quantum field theory living on its lower dimensional boundary. This means that a process involving gravity and the loss of energy in our 3-dimensional world could be perfectly mirrored and perfectly conserved in a gravity-free quantum description on a distant surface. The energy is not lost, it is merely translated into a different language on a different plane of reality. In string cosmology, these ideas take on a life of their own. As our universe expands, the hidden extra dimensions might not be static. They could be compactifying, tightening their curl, or even evolving in their own right. This dynamic process would directly affect the cosmic energy budget. The energy that seems to vanish from our view as light redshifts could be shifting into these unseen dimensions, a cosmic sleight of hand where the energy is not destroyed, but simply moves where we cannot measure it. This leads to the mind-bending concept of brain worlds. Imagine our entire universe, with all its galaxies and stars, is not a free-floating 3-dimensional volume, but a membrane or a brain, existing within a higher dimensional expanse called the bulk. We are stuck on our brain, unable to perceive the full bulk, like ants living on a single page of a vast book. In this scenario, the gravitational force, and perhaps its associated energy, could be the only thing that leaks off our brain and into the bulk. The work done by the expansion of our universe, the energy seemingly lost, might be radiating away into these extra dimensions. It is like living in an apartment in a towering skyscraper. You can measure the energy in your own apartment, but if heat leaks through the floor or ceiling into the apartments above and below you, your personal energy ledger will show a deficit. The energy is not gone from the building, it has just moved to another floor. This framework gives rise to models like the pre-Big Bang scenario, where our universe's birth was preceded by a phase of inflation in a higher dimensional realm. It also allows for cyclic universes where the cosmos goes through an endless sequence of expansions and contractions. In these models, the energy is never truly lost. At the end of a cycle, when the universe collapses into a fiery crunch, all the redshifted energy and matter is recycled, melted down and forged anew for the next Big Bang. The ledger is balanced not in a single universe but over an eternal cycle of cosmic rebirth. So, could quantum gravity finally reveal where the energy goes? It suggests that our three-dimensional accounting is inherently incomplete. We are trying to balance the books for a single branch of an infinite, multidimensional corporation. This profound shift in perspective naturally opens the door to an even grander possibility, that our entire universe is just one bubble in an endless, frothing multiverse. Our universe could be just one bubble in an infinite cosmic foam. This is the Multiverse Hypothesis, a staggering idea that redefines the scope of reality itself. According to cosmologist Max Tegmark, this multiverse could exist on multiple levels, from the infinite regions beyond our cosmic horizon to universes with entirely different physical laws and constants. In this vast ensemble, our universe is not special or alone. It is one member of an unimaginable population, each with its own unique properties. Within frameworks like eternal inflation or the string theory landscape, new bubble universes are constantly nucleating and expanding, budding off from a primordial, inflating background. In such a dynamic, multi-realm cosmos, energy might not simply vanish. It could be transferring elsewhere, leaking across the boundaries between universes. Our cosmic ledger, which appears unbalanced from our isolated viewpoint, might be perfectly balanced across the entire multiverse. The expansion of our own universe could be the very mechanism enabling this leakage, a conduit for energy to flow into the broader cosmic landscape. This process could occur through vacuum decay or quantum tunneling, where the fabric of our spacetime quantum mechanically connects to another realm, allowing a subtle energy exchange. Think of a series of interconnected ponds. Our universe is one pond. We see the water level dropping and assume water is being destroyed, but in reality, the water is simply flowing through hidden channels into the other ponds. The entire system conserves water, even if our local pond does not. This analogy illustrates how energy could be conserved globally across the multiverse while appearing to be lost from our local, observable universe. The implications for dark energy are profound. The mysterious force accelerating our expansion might not be a fundamental property of our vacuum, but a local side effect of this multiverse dynamics. Our universe's specific value for the cosmological constant, that tiny, puzzling number, could simply be an environmental artifact, one value among a near-infinite spectrum of possibilities in the wider landscape. This offers a potential, though controversial, solution to the cosmological constant problem. The constant is not fine-tuned. We just happen to live in one of the rare bubbles where its value allows for galaxies, stars, and life to form. The challenge, of course, is testing such an idea. How do you observe a universe beyond your own? Some scientists have looked for possible evidence in the cosmic microwave background, searching for anomalies like unusual cold spots that could be imprints of a collision with another bubble universe in the distant past. These are faint, speculative hints, but they represent the extraordinary lengths we must go to investigate such a radical proposal. So, does the multiverse truly solve the ledger problem? Philosophically, it offers an elegant escape, externalizing the problem to a realm beyond observation or disproof. Yet it also forces us to accept that the most fundamental laws we seek to understand might only be local bylaws, valid in our cosmic neighborhood but irrelevant in the grander scheme of things. Our search for a balanced ledger leads us to a humbling possibility that we are not just reading the accounts of a single company, but trying to understand the finances of an entire, invisible conglomerate. This cosmic energy leak strikes at the very heart of our desire for a predictable, orderly universe. We have long clung to the principle of causality, the idea that every effect must have a cause and that the universe operates by a consistent, reliable set of rules. But if energy is not conserved on the grandest scale, what does that say about the permanence of these rules themselves? The philosopher Karl Popper championed the idea of falsifiability as the cornerstone of science. A scientific theory must make predictions that can, in principle, be proven wrong. Our long-held belief in the global conservation of energy was one such theory, a pillar of physics. The expanding universe, with its disappearing photons, appears to have falsified it. This forces us to ask a deeply unsettling question. Are the laws of physics we have discovered truly fundamental, eternal truths? Or are they merely local bylaws, temporary regulations that hold true in our cosmic neighborhood but break down when applied to the whole? This dilemma ignites a classic debate between realist and instrumentalist views of science. A realist would argue that energy is a real, physical quantity that exists in the world, independent of our measurements. Its apparent non-conservation is a problem to be solved, a clue pointing to a deeper reality we have yet to grasp. An instrumentalist, however, might say that energy is not a thing in itself, but merely a useful calculation tool, a number that helps us make accurate predictions in our laboratories. From this perspective, the cosmic ledger problem is not a crisis, but a sign that our tool is no longer fit for purpose on a universal scale. It is like using a yardstick to measure the ocean, a useful instrument in a bucket of water, but meaningless when applied to the entire sea. This crisis of conservation even challenges the principle of sufficient reason, the philosophical idea that everything must have a reason or a cause. If energy does not need to be conserved, could the universe itself have simply popped into existence from nothing without a cause? The zero-energy universe hypothesis we explored earlier fits neatly into this idea, suggesting a grand cancellation that requires no initial input. Think of it as the ultimate magic trick. A magician shows you an empty hand, then opens it to reveal a coin. You saw the empty hand, you saw the coin appear. Your mind insists a trick was played, that the coin was hidden somehow. But what if, for the universe, there was no trick? What if the cosmos is simply that kind of place, where things can happen without a strict, causal chain of energy conservation? This reshapes our entire cosmic worldview, moving us from a vision of a clockwork universe, wound up and ticking predictably, to one of a living, breathing, and fundamentally creative entity. The implications ripple into our understanding of time and eternity. If the universe is not a closed system with fixed energy, then its story may not be a simple, linear narrative of birth, life, and heat-death. It could be a chapter in a much larger, more dynamic book, with energy flowing in and out of the narrative in ways we cannot yet perceive. Even the anthropic principle, the observation that our universe seems finely tuned for life, takes on a new light. If energy conservation is not a strict universal law, then one of the key constraints on what a universe can be is loosened. The specific conditions that allow us to exist might be more flexible or more common in a multiverse where the ledger is balanced across countless realities. This is not just abstract philosophy, it has practical stakes. Our entire technological civilization is built upon the reliable conservation of energy. From the power grid to rocket science, we trust that energy transformations are predictable and accountable. The cosmic ledger problem does not invalidate that local trust, but it does hint that the ultimate foundations of our engineering may have a crack running through them. Understanding this crack could one day lead to technologies we can scarcely dream of, perhaps ways to interact with the fabric of space-time itself, not as passive observers, but as participants in the cosmos's creative, and sometimes profligate, energy accounting. The universe's disappearing energy is not just a theoretical puzzle. It is a problem with profound practical consequences, shaping the very tools we use to explore the cosmos. While we cannot plug a cable into space-time to recharge our batteries, understanding this cosmic energy leak is already refining our technology and guiding our search for deeper truths. Consider the silent conversation we maintain with our robotic ambassadors across the solar system. NASA engineers must account for a multitude of effects to communicate with probes like Voyager, which now sails through interstellar space. The signals we send and receive are affected by the Doppler shift from the craft's motion, but on much longer intergalactic timescales, the cosmological redshift itself would become a factor, subtly draining the energy of every photon carrying our data. Correcting for this loss is essential for interpreting the faint whispers from the edge of our vision, ensuring that a weak signal is understood as a distant message, not a dying battery. This cosmic accounting also fuels revolutions in simulation. To model the universe, we must first understand its rules, and the ledger problem sits at the heart of this effort. In supercomputers around the world, physicists run complex models of cosmic evolution, simulating how dark energy and gravity sculpt the large-scale structure of the cosmos. These are not mere academic exercises. The algorithms that power these simulations share a family resemblance with those being developed for quantum computing. A future quantum computer could, in theory, simulate the fabric of an expanding universe with a fidelity impossible today, explicitly testing how energy flows or appears not to flow in a dynamic spacetime. Such a simulation would be the ultimate cosmic laboratory, allowing us to run experiments on the birth of galaxies and the fate of light, providing insights that could crack the ledger wide open. The most tantalizing application, however, lies in the realm of energy itself. The confirmed existence of vacuum fluctuations, demonstrated by the Casimir effect, proves that empty space is not empty. It is a seething reservoir of quantum activity. Could we ever learn to tap this cosmic energy reserve? The challenge is monumental, like trying to bottle lightning from a silent, invisible storm. The energy is there, but it is random, fleeting, and evenly distributed, making it extraordinarily difficult to extract useful work. Yet the pursuit drives fundamental research. Understanding how the expanding universe promotes virtual particles into real ones might one day inspire a radical new principle for energy generation, a technology that works with the geometry of spacetime rather than against it. These insights ripple into surprisingly terrestrial domains. The global positioning system is a daily testament to the practical necessity of Einstein's relativity. The satellites in their orbits experience time slightly differently than we do on Earth, and without precise corrections for these relativistic effects, GPS would fail within minutes, its navigation data drifting by kilometers. Our refined cosmological models, born from struggling with the ledger problem, operate on the same principle. They provide a more accurate map of cosmic forces, which in turn improves our understanding of how Earth's climate fits into the broader planetary context. By modeling energy flow on a universal scale, we gain a deeper appreciation for the delicate balances that sustain our own world. Could solving this ancient mystery ultimately unlock new energies? The path is uncertain, but the direction is clear. Each step toward understanding the cosmic ledger is a step toward a deeper mastery of the physical world. It transforms our relationship with the universe from that of a passive observer to an active participant, learning to read the fine print in the laws of reality. This journey does not end with a single equation. It sparks a continuous cycle of inquiry, pushing the boundaries of education and public wonder, inviting everyone to ponder the same fundamental questions that have captivated physicists for a century. Teaching the cosmic ledger problem requires a delicate balance, presenting profound mysteries without overwhelming young minds. The key is to build from the familiar, anchoring cosmic weirdness in tangible experiences. Start with a simple rubber band, stretch it and draw a wave on its surface, representing a photon of light. As you pull the rubber band longer, the wave stretches out, its peaks and troughs moving farther apart. This is the cosmological redshift in your hands. The wave is now longer, and just like a red light photon carries less energy than a blue one, the stretched wave on the rubber band represents a direct loss of vigor. The energy did not go to the rubber band, it simply faded as the canvas expanded. This simple analogy makes an abstract loss concrete. Neil deGrasse Tyson often champions this approach, arguing that cosmic literacy is not about memorizing facts, but about fostering a mindset of inquiry. He suggests that understanding our place in a dynamic, energy-leaking universe is fundamental to modern scientific literacy, transforming citizens from passive observers into active participants in the human journey of discovery. In classrooms, hands-on activities bring the math to life. A classic exercise uses a partially inflated balloon with dots marked on it to represent galaxies. As students blow more air into the balloon, they watch every dot move away from every other dot. No one dot is the center. This model perfectly illustrates the expansion of space itself. Now ask them to draw a line connecting two dots, representing a beam of light. As the balloon expands, the line stretches, visually demonstrating how the light's wavelength elongates and its energy diminishes, diluted by the growing surface area of their miniature cosmos. This physical model bridges the gap between an equation on a page and the physical behavior of the universe. Integrating these concepts into standard physics curricula creates powerful connections. When students learn the first law of thermodynamics, the conservation of energy, they can immediately be presented with its greatest exception. This does not undermine the law, it enriches it, showing that science is a living, evolving process. The lesson can link directly to modern standards on relativity, demonstrating how our models must adapt when moving from the laboratory to the cosmos. Digital tools amplify this understanding. Interactive universe simulators allow students to slide a timeline from the Big Bang to the present, watching not only galaxies drift apart, but also seeing the color of background light shift from brilliant blue to deep red as its energy drains away. They can tweak the amount of dark energy and witness the dramatic effect on the cosmic energy budget, making the abstract concept of a cosmological constant something they can manipulate and explore. Public understanding thrives on this same sense of wonder. Planetarium shows are perfect venues for this story. A domed screen can visually transport an audience on a photon's billion-year journey, making them feel the gradual, inexorable loss of energy as the space between galaxies stretches. A skilled presenter can pause the simulation at the moment a photon from a distant quasar finally arrives at our telescope, its energy a faint echo of its former self, and pose the very question that drives cosmology forward. Where did its power go? This kind of storytelling does not offer easy answers, but it ignites the curiosity that seeks them. The ultimate success of this educational effort is measured in the sparks it ignites. Consider a high school student initially puzzled by the balloon analogy, who stays after class to ask more questions. She starts reading about Noether's theorem and the symmetries of space-time, her confusion transforming into a driving need to understand. That student grappling with the paradox of the cosmic ledger is not just learning physics, she is developing the tenacity and imagination that could one day solve the mystery. How do we inspire the next generation of ledger solvers? We give them the puzzle in all its beautiful, unresolved grandeur, and trust that the human drive to find answers will do the rest. This open-ended challenge naturally leads us to the most thrilling part of the story, the cutting-edge experiments and bold theories that are actively hunting for a solution. The case of the cosmic ledger remains wide open, with clues scattered across the universe and no single theory yet holding the master key. The central enigma persists: does a full theory of quantum gravity, one that successfully unites general relativity with quantum mechanics, promise to restore perfect energy conservation, or will it force us to accept its loss as a fundamental feature of reality? Physicist Lee Smolin has argued that resolving these deep cosmological puzzles, including the fate of energy, demands just such a complete theory. Until we understand how space-time is woven from discrete quantum threads, our accounting will remain provisional. This pursuit defines the cutting edge of cosmology, with several critical questions guiding the hunt. Is the constant density of dark energy a profound clue, pointing to a vacuum energy that defies classical bookkeeping? Do the ripples of gravitational waves, which carry energy across the cosmos, also transport some of this missing energy away from our local balance sheet? And most explosively, how does the energy budget of cosmic inflation, which seemingly created a universe from a quantum fluctuation, ever truly balance? Researchers are now designing experiments to chase these mysteries. Gravitational wave observatories are not just listening for the collisions of black holes, they are testing the very fabric of spacetime. When two black holes spiral inward and merge, the immense energy they radiate as gravitational waves could provide a unique laboratory. By comparing the mass energy lost by the system to the energy carried away by the waves, scientists can search for tiny discrepancies, for any hint that energy is not being perfectly conserved in these most extreme gravitational events. Future missions are poised to deepen the investigation. The James Webb Space Telescope, by peering back at the earliest galaxies, is effectively measuring the energy conditions of the young universe. Its observations could reveal how quickly dark energy began its influence, and whether the energy drain from light has followed the precise timeline our models predict. Even more tantalizing is the hunt for a faint, primordial background of gravitational waves, a relic signal from the inflationary epoch. Detecting this whisper would be like finding the original energy receipt from the Big Bang's initial expansion, showing us directly how energy was transferred from the inflatoned field into the very fabric of spacetime, creating the seeds of all structure. This is a cosmic detective story where the clues are written in redshifted light, in the subtle patterns of the cosmic microwave background, and in the silent ripples of gravity. The case file is thick with data, but the final page remains unwritten. What breakthrough might finally close the ledger? It could be a revolutionary observation from a new telescope, a brilliant mathematical insight that redefines energy for an expanding universe, or a laboratory experiment that detects the quantum structure of spacetime itself. Each possibility promises to reshape our standard model of cosmology, forcing us to rewrite the textbooks on how the universe truly manages its accounts. Our most successful map of the cosmos is beginning to show cracks under the weight of this mystery. The Lambda-CDM model, the standard blueprint of modern cosmology, assumes a universe where energy and matter are conserved on the largest scales. Its very name encodes its key ingredients, lambda for dark energy and CDM for cold dark matter. This model is spectacularly successful, predicting the cosmic microwave background and the large-scale distribution of galaxies with stunning accuracy. Yet the cosmic ledger problem presents a direct challenge to its foundation, suggesting the model's elegant equations might be missing a crucial term, one that accounts for the energy seemingly draining from the cosmos. Experts within the Planck collaboration and other groups have long noted a growing tension, particularly in measurements of the Hubble constant, the rate of the universe's expansion. Different methods yield stubbornly different results. Could this Hubble tension be a subtle signal of the missing energy, a hint that our cosmic accounting is slightly off? If energy is not globally conserved, it would force us to modify the model's parameters or introduce entirely new physical fields. Think of the lambda CDM model as the architectural plan for a magnificent, ever-expanding building. The plan works beautifully for describing the walls and the rooms, the galaxies and the dark matter halos, but the builders keep noticing a strange draft, a persistent leak that the original blueprints do not account for. The cosmic ledger problem is that draft. It suggests the building itself is slowly losing heat, and we need to revise the plans to understand where it is going. One potential revision is to replace the static cosmological constant with a dynamic form of dark energy like quintessence. This would introduce a new, evolving field into the model, one that could potentially interact with matter and radiation, allowing for a more complex flow of energy that might restore a form of conservation under a new set of rules. Alternatively, the solution might lie in altered gravity, modifying Einstein's equations to account for the energy loss inherently. Each of these extensions has consequences. They change the model's predictions for how quickly the universe expands, how galaxies cluster into vast filaments and walls, and even the estimated age of the cosmos. If energy is genuinely being lost, then the universe's expansion history would be different than we currently calculate. The clock of cosmic time would tick a little differently. The light from the most distant supernova would carry a faint, additional imprint of energy depletion, subtly altering their apparent brightness and distance. Fitting these revised models to the exquisite data from galaxy surveys and the cosmic microwave background becomes a high-stakes test. Does a model that explicitly allows for energy non-conservation provide a better fit to the observed large-scale structure of the universe? Does it resolve the nagging Hubble tension? The answers are not yet clear, but the pursuit is pushing cosmology toward a potential revolution. The standard model is robust, but it may not be complete. The ledger problem forces us to ask if we are merely adding epicycles to an old paradigm, or if we are on the verge of a deeper understanding that will redefine our most fundamental concepts of energy, time, and space. This search for a more complete theory inevitably leads us into the abstract language of mathematics, where the true secrets of the cosmos are often first revealed. Mathematics provides our most powerful tools for this cosmic accounting, yet it reveals the problem's deep roots. To even begin quantifying energy in an expanding universe, physicists must turn to sophisticated formalisms like the idiom approach, named for its creators Arnold, Désir, and Misner. This framework slices the four-dimensional fabric of spacetime into a sequence of three-dimensional moments, like frames in a cosmic film reel. On each slice, we can attempt to define a total energy. But this definition is not absolute. It depends entirely on the chosen observer and the boundary of the slice. The mathematician Yvonne Choquet-Bruhat, a pioneer in general relativity, articulated the core difficulty, noting that in a curved and dynamic spacetime, there is no unique or natural way to define a global energy for the entire system. The very geometry we are trying to measure is itself in flux. One classic tool is the comma integral, a mathematical formula designed to calculate the total mass energy within a region of space. It works beautifully for static systems, like a lone, non-rotating black hole suspended in an otherwise empty and unchanging universe. But introduce expansion, and the comma integral fails. It relies on the existence of a special structure called a time-like killing vector field. Think of this as a mathematical representation of a perfectly uniform flow of time throughout space, a guarantee that the universe looks the same from one moment to the next. Our expanding cosmos has no such uniformity. Time flows differently as space stretches, breaking the symmetry that the comma integral needs to produce a single, conserved number. This is like trying to measure the length of a rubber band with a ruler that is itself stretching at an unpredictable rate. Your measurement becomes ambiguous, dependent on when and how you choose to measure. This is the fundamental ambiguity of energy in cosmology. Without a time-like killing vector, there is no natural, conserved energy definition for the universe as a whole. Physicists have developed more flexible tools to work around this, such as the concept of quasi-local energy, developed by James York and later refined by Brown and York. Instead of trying to sum up the energy of the entire cosmos, quasi-local energy calculates the energy contained within a finite, two-dimensional boundary. Imagine drawing a sphere around a region of space. The Brown-York energy gives you the total energy inside that sphere, but it crucially includes contributions from both the matter within and the gravitational field on the boundary itself. This approach is incredibly useful for studying black holes or even our own cosmological horizon, yet it still does not solve the global ledger problem. The energy within one bubble does not have to match the energy within another, because the work done by expansion can transfer energy across these boundaries in ways that are not tracked. Even Noether's theorem, the very source of energy conservation, must be applied in a modified, more limited form. The theorem connects symmetries to conservation laws, but in a universe without global time translation symmetry, physicists must search for approximate or asymptotic symmetries. They look at the very boundaries of the observable universe at infinity and ask if the geometry there still has some vestige of symmetry that could define a conserved quantity. In an accelerating universe dominated by dark energy, the answer is often no. The de Sitter horizon, the ultimate edge of our vision, does not provide the clean symmetries needed to rescue global energy conservation. So where does this leave our accounting? These mathematical formalisms do not close the ledger. Instead, they formalize the leak. They provide a precise language for describing how energy depends on the observer's perspective and the chosen cosmic yardstick. They confirm that the energy lost by a redshifted photon is genuinely absent from our global sums, a casualty of a spacetime geometry that refuses to stand still. This mathematical ambiguity is not a failure. It is a guidepost directing us toward the only place we can test these wild ideas, inside the virtual universes of supercomputers. These vast digital universes are born inside the world's most powerful supercomputers. Computational cosmologists build entire realities from scratch, not with telescopes, but with millions of lines of code. Programs like Gadget and ENSO take our best physical theories and use them to choreograph the birth and evolution of billions of particles, representing dark matter, gas, and stars across billions of virtual years. They are our ultimate cosmic laboratories for testing the ledger problem, allowing us to watch energy flow and fade in ways we could never observe directly. Volker Springel, a leading architect of these simulations, notes that they reveal how energy is redistributed on the grandest scales, particularly within the violent mergers of galaxy clusters where gravitational potential energy is converted into heat and light with staggering force. These codes meticulously track the journey of virtual photons as they travel through the expanding digital space. Each photon's wavelength is stretched by the simulated cosmic expansion, its energy steadily decreasing, just as we observe in the real universe. Simultaneously, the simulation calculates the changing gravitational potential energy of every particle as they are carried apart by the Hubble flow. The results are both revealing and deeply puzzling. When researchers run the numbers, adding up all the kinetic energy from motion, the mass energy from particles, and the radiation energy from light, the total is not a constant. It fluctuates and trends downward over cosmic time. The energy simply does not conserve itself in these virtual universes. This is not a programming error. It is a direct consequence of the simulated expansion. As the digital space stretches, the gravitational potential energy of the simulated structures increases, but there is no corresponding drop in kinetic energy to balance it out. The work done by the expansion injects energy into the system in a way that our classical bookkeeping cannot neatly capture. The simulations show that in the formation of a massive galaxy cluster, the gravitational potential energy becomes deeply negative as matter collapses. Yet the overall sum of this energy, when combined with the energy of the expanding background, still does not remain constant. There are inherent limitations to this digital approach. The finite resolution of the simulation means that small-scale physics, like the intricate dynamics of individual stars or the quantum vacuum, is lost in the pixelation. Furthermore, defining a global energy for the entire simulation box is a formidable challenge. The simulation has boundaries, an edge that the real universe does not have, and how you treat the energy at that artificial edge can influence the entire accounting. Despite these constraints, the message from countless digital runs is clear. In a universe governed by general relativity and dark energy, our conventional sum of all energy is not a sacred, unchanging number. It is a fluid quantity shaped by the evolving geometry of spacetime itself. This forces us to confront a profound question. If our most accurate models of reality consistently show energy non-conservation, are we witnessing a flaw in our models or a fundamental truth about the cosmos? The answer may lie not in the energy of the cosmos, but in the information required to describe it. This fundamental uncertainty in the cosmic ledger echoes a very human conversation about our own planet's resources. If the universe itself cannot be relied upon to conserve its most fundamental currency, what does that say about our frantic efforts to sustain a finite world? The environmental thinker Bill McKibben, invoking the precautionary principle, argues that when faced with systems of immense complexity and potential irreversibility, the burden of proof should fall on those who propose radical intervention. The cosmos presents us with a similar lesson on a grand scale. We are tampering with Earth's climate, a system we do not fully understand, while simultaneously discovering that the foundational laws we thought governed all of reality are not what they seemed. This cosmic humility should not breed apathy, but a more profound sense of responsibility. The universe may be profligate with its energy, but we, on our small, fragile world, do not have that luxury. We must steward what we have with immense care, precisely because we are not the center of a predictable, mechanical clockwork, but inhabitants of a dynamic, creative, and perhaps even wasteful cosmos. This perspective directly fuels the need for robust scientific funding, unraveling how the universe manages or mismanages its energy budget is not an esoteric pastime. It is a fundamental inquiry that sharpens our understanding of energy itself, from the quantum vacuum to the power grid. Research into dark energy and cosmic expansion, for instance, pushes the boundaries of our mathematical and computational tools. These advances often ripple into practical technologies, just as the struggle to understand thermodynamics birthed the steam engine. Understanding how energy is lost or transformed on a cosmic scale can inform new approaches to energy efficiency and waste heat management in our own industrial processes. Yet, this profound mystery also carries a risk of misinterpretation. The same cosmic puzzle that inspires genuine scientific wonder can be twisted into pseudoscientific claims of free energy devices, promising to tap into the universe's disappearing power. Such ideas misunderstand the crucial distinction between a global cosmological effect and local physical laws. While energy may not be conserved for the entire universe, the first law of thermodynamics holds absolutely firm within your home, your car, and every piece of technology we use. Attempting to bypass it with gadgets based on a misreading of cosmology is a path to dead ends. This highlights the critical need for a scientifically literate public, capable of engaging in nuanced discourse about what these discoveries truly mean and what they do not. Ultimately, the cosmic ledger problem is more than a physics puzzle. It is a philosophical and ethical touchstone. It connects the vast, impersonal mechanics of the expanding universe to the intimate, urgent challenges of sustainability on Earth. It teaches us that our models of reality are provisional, that wonder is a valid and vital response to the unknown, and that our pursuit of knowledge for its own sake is what ultimately equips us to navigate an uncertain future. This interdisciplinary bridge, linking the fate of photons across the void to the choices we make in our daily lives, reveals that the greatest value of the mystery may not be the answer we eventually find, but the deeper questions it forces us to ask about our place in a profoundly strange cosmos. This energy conundrum reaches far beyond astrophysics, weaving its way into the very fabric of human thought and creativity. The question of whether the cosmos conserves its energy is not merely a technical one. It forces a deep philosophical reckoning with the nature of reality itself. If our most trusted physical law is not a universal constant but a local ordinance, what does that say about the permanence of any rule? Philosophers grapple with this, debating whether a universe without strict energy conservation is one of pure chance or of a different, more complex kind of order. The physicist and writer Carlo Rovelli beautifully articulates this bridge, suggesting that questions about time and energy are where the sharp lines between science and the humanities begin to blur. He writes that our struggle to understand these cosmic fundamentals is at its heart a deeply humanistic endeavor, connecting our fleeting existence to the grand architecture of spacetime. This connection becomes strikingly clear in the realm of information theory. Here, energy and information are inextricably linked through Landauer's principle, which states that erasing a single bit of information must always dissipate a tiny, specific amount of heat energy. It establishes a fundamental exchange rate between the abstract world of data and the physical world of thermodynamics. Now, project this principle onto a cosmic scale. As the universe expands and light redshifts, losing energy, is the universe effectively erasing information? Is the fading of a photon's vigor equivalent to the loss of a cosmic bit? The relentless expansion might be imposing a fundamental limit on the total information content the cosmos can preserve, a slow, cosmological data decay written in the light of distant galaxies. These abstract ideas find practical and beautiful expression. Computer scientists developing algorithms to manage vast, flowing datasets often draw inspiration from cosmological models. They see parallels between the way energy behaves in an expanding universe and the way computational resources must be managed in a distributed network, where information can seem to dilute across growing digital spaces. Artists, too, are captivated by the metaphor. Imagine an immersive installation where a field of suspended lights represents a galaxy cluster. As visitors walk through, motion sensors trigger a gentle, continuous expansion of the lights, their brilliant white glow slowly shifting to a deep, dim red. This sensory experience makes the abstract loss of energy palpable, translating a billion-year process into a moment of quiet awe. Composers have scored symphonies using the mathematical rhythms of cosmic inflation, the music swelling and fading to mirror the universe's own breath. In literature, a novelist might use the cosmic ledger problem as a powerful plot device, crafting a story where something essential, memory, love, even time itself, is slowly draining away, mirroring the photon's journey across the void. Each of these disciplines adds a unique color to the tapestry of our understanding. Philosophy questions the foundational assumptions. Information theory provides a new currency for the accounting. Art offers a visceral, emotional connection to the mystery. No single thread holds the complete picture. True progress in solving the cosmic ledger may depend on this very collaboration, on physicists speaking with poets and coders sharing insights with cosmologists. The next breakthrough might not come from a telescope's lens alone, but from a conversation that bridges the laboratory, the studio, and the supercomputer, weaving their collective insights into a new vision of reality. The next generation of cosmic cartography is already underway, aiming to map the invisible architecture of our expanding reality. The European Space Agency's Euclid Telescope and NASA's forthcoming Nancy Grace Roman Space Telescope are not merely new eyes on the sky. They are precision instruments designed to take the universe's financial audit. As one Euclid project scientist explains, their primary goal is to constrain the equation of state of dark energy, that critical number which tells us whether dark energy is a true constant or something that evolves over time. By measuring the shapes and distributions of billions of galaxies across cosmic history, these missions will trace the expansion of the universe with unprecedented fidelity, revealing exactly how the stretching of space has accelerated over billions of years. This data will directly test our models of energy conservation, or the lack thereof. If the energy loss from redshifted light is a real physical effect, it will leave a specific imprint on how structures form, an imprint these telescopes are exquisitely designed to detect. Beyond the silent gaze of telescopes, a new sense is developing to listen to the cosmos. The Laser Interferometer Space Antenna, or LISA, will open the gravitational wave spectrum to low-frequency sounds, hearing the mergers of supermassive black holes and the ripples from the universe's earliest moments. When two black holes spiral together, they shake the fabric of spacetime, radiating immense energy across the cosmos. LISA will measure these events with such precision that scientists can compare the energy radiated away as gravitational waves with the mass energy lost by the system. Any tiny discrepancy could be a smoking gun, a direct measurement of energy subtly leaking from the most violent events in the universe into the expanding background. This is not just observing the ledger, it is watching the transactions happen in real time. Parallel to these observational leaps, theoretical frontiers are pushing deeper into the abstract. The quest for a full theory of quantum gravity continues, with string theory and loop quantum gravity offering competing visions of how spacetime is woven at the smallest scales. Within these frameworks, the concept of energy is being completely redefined. New, more powerful cosmological simulations are also being built, running on next-generation supercomputers that can model not only dark matter and galaxies, but also the complex feedback of magnetic fields and radiation. These digital universes will allow us to track the flow of energy with a fidelity that mirrors reality, searching for the precise moment when the cosmic balance sheet begins to drift. Even the public is being invited to join the hunt. Citizen science projects will allow anyone with an internet connection to help astronomers sift through the torrent of new data, classifying unusual galaxies or searching for subtle anomalies in the light from distant quasars that might hint at unexpected energy loss. The ultimate clues may be etched into the oldest light of all. Future observatories focused on the cosmic microwave background will look for faint, twisted patterns known as B-modes, which could carry the imprint of primordial gravitational waves from the inflationary epoch. If detected, these patterns would tell us directly how much energy was pumped into the universe during its initial violent expansion, providing a crucial data point for the very first entry in the cosmic ledger. We are charting a course into territories as vast and unknown as the oceans were to ancient explorers. Every precise measurement, every new theoretical insight, and every pair of eyes helping to analyze the data brings us one step closer to answering the fundamental question. Does the universe keep perfect books, or is its apparent extravagance with energy the deepest clue we have to its true nature? This long journey of cosmic inquiry ultimately brings us back to our own place within this magnificent, mysterious, and perhaps profligate cosmos. I remember the first time I truly grasped that energy might not be conserved. It was not in a lecture hall or while reading a dense textbook. It was on a quiet beach watching the sunset. As the sky blazed with orange and red, a simple, staggering thought arrived. Each photon of that brilliant light had traveled from the sun, and during its 8-minute journey, the space it moved through had stretched just a little. Every single ray of that beautiful sunset was arriving at my eyes with slightly less energy than when it began. That minuscule loss, multiplied by the countless photons painting the sky, was a direct personal connection to the cosmic ledger. It was no longer an abstract theory, but a quiet, constant process happening right in front of me. That feeling was not one of confusion, but of profound awe. It was a humbling reminder that our most trusted laws are not absolute monarchs ruling the cosmos, but more like local guidelines, perfectly reliable in our everyday world, yet bending and shifting when faced with the grand, dynamic stage of the universe. This is the central insight we must carry forward. The apparent disappearance of energy in expanding space is not a bug in Einstein's general relativity. It is a fundamental feature. The universe is not failing to keep its books. We are simply using the wrong accounting system for the job. This enigma is not a dead end. It is the very engine that drives cosmology forward, pushing us to build better telescopes, dream up wilder theories, and peer deeper into the quantum foam. The history of science is written in these moments of broken intuition. Every time we discover a limit to our knowledge, we are not facing a wall, we are finding a doorway. The cosmic ledger problem teaches us to embrace uncertainty, to question the established laws we take for granted, and to find wonder in the gaps of our understanding. That sense of wonder is the most practical tool we have. The next time you feel the warmth of sunlight on your skin, consider the incredible journey of those photons. They are not just bringing you light and heat, they are carrying a message from the heart of a star, a message that has been subtly altered by the fabric of the cosmos itself. That daily, ordinary experience is a miniature cosmic ledger, a tiny piece of the universe's grand, mysterious accounting. How will you carry this question forward? Let it change the way you see the world. Let it remind you that the universe is far stranger and more magnificent than we can often perceive, and that the greatest discoveries begin not with answers, but with a courageous, humble question. So the cosmic ledger remains open, a permanent entry in the great book of unsolved mysteries. This journey began with a simple, unsettling observation that light from distant galaxies is not just receding, but losing its very essence as space stretches. We followed this disappearing energy from the warped geometry of general relativity to the phantom pressure of dark energy, from the seething quantum vacuum to the holographic boundary of reality itself. At every turn, the first law of thermodynamics, so absolute in our labs, met its match in the expanding cosmos. Yet this is not a story of failure, but of profound evolution. The missing energy challenge does not break our understanding of physics. It deepens it, forcing us to see the universe not as a static stage, but as a dynamic, creative, and fundamentally unpredictable entity. Carl Sagan once reminded us that somewhere, something incredible is waiting to be known. That something is the true nature of cosmic accounting, a secret hidden in the fabric of space-time, in the whisper of gravitational waves, or in the quantum structure of the vacuum. This puzzle invites you to look at the night sky with new eyes, to see the fading light of stars not as a loss, but as a question. How does this change your own relationship with energy, with the idea that the most fundamental rules might be local, not universal? If you found this exploration as captivating as we did, consider subscribing to continue this journey with us into the heart of space's greatest mysteries. Share this video to spark a conversation, to spread a little cosmic wonder, and let us know in the comments where you think the lost energy has gone. The universe is not a puzzle to be solved, but a mystery to be explored, and your curiosity is the most